Alright, we've talked a bit about Ksp, the solubility product constant of salts or ionic compounds, but we also want to discuss other ways to quantify how well a salt dissolves. And we're going to look at solubility and molar solubility. They're very simple concepts, but to go from one way to quantify to another could be a little bit tricky. But for this video, I want to go over some of the definitions. And actually, before we go over any definitions, let me remind you what you know and what you can do in the lab. You have, for instance, a beaker. Oh, we could call this cartoon. You have a beaker and you have water. Let's say we have maybe 1,000. No, that's too much. Yep, 1,000 grams of H2O. And you start dumping in solid. So you have solid out here, and you're going to dump it in here. Well, if the solid has limited water solubility, then you'll start to quickly form or precipitate. But yeah, there is some that could be soluble. What are we used to? Before we even learned about Ksp, we were used to solubility charts. And for instance, we added maybe 1 gram of this, 2 grams of this, but maybe by the 3rd gram we started to see precipitate. So we could say something like, these are made up numbers, but calcium hydroxide maybe has a solubility of, let's say, 0.62 grams per liter. Okay, so you're used to those units, grams per liter. Well, we could get what's called a molar solubility, right? Molar solubility. If you think about the term molar, then it's going to be in moles per liter. We already have liters here. So we could just multiply. Is that going to be right? Multiply? No, divide. Divide by the molar mass. And we could get a molar solubility. You also learn terms such as, well, if you start to see it precipitate, your solution is saturated. Abbreviation for precipitate is PPT. If you see it precipitate, then your solution is saturated. And if you don't, then the solution is unsaturated, and you could keep dissolving more. If you don't see precipitate, that's unsaturated. And what can you do? You can add more solid. Think back to Ksp. Think back to Q. What did I just describe in this purple writing? I described a situation, unsaturated, where the Ksp is less than the Ksp. And we need to make more ions, right, by dissolving more solid to get the Q to be equal to Ksp. And then if we keep adding more solid, well, we're going to get Q that's greater than Ksp. Q that's greater than Ksp. And we have to go in the reverse direction. All right. Keep that in mind. Let me give you your formal definitions, and we'll do. We're not going to do any calculations here, but we are going to set up the equations, the chemical equation, the Ksp, and also solubility and molar solubility. Okay. Are we going for units? Definitions and units. The next video we will do calculations using these concepts. Ksp, we better have an equation. Let's just do AgCl, solid, Ag plus. From our solubility rules in Gen Chem 1, silver chloride is not that soluble, so it will have a Ksp. The Ksp, again, that's called the solubility product. We're literally multiplying the products together, constant. Solubility, solubility, product constant. Ag plus, there's no coefficient, so don't put an exponent, Cl minus, and we're good. That's Ksp. What is solubility? Simply, it's how much you can dissolve before you get a precipitate. Now, I am interchanging the terms dissolve, dissociate, ionize. So the same thing as dissolve, we're going to say, for this purpose, say dissociate. How much can dissociate? How much can separate um, before you get a precipitate? Okay. Next. Oh, and also, um, I tried to be a little bit fancy. In brackets or in parentheses is the abbreviation. So little s for solubility, big S, capital S for molar solubility. Ooh. It's little s and it's in grams per liter. And then big S. Big S is molar solubility. I'm getting better at saying that. And that unit is in moles per liter. Okay. Let us set up. Oh, do I need to do anything here? Yes. Okay. So this is a little bit tricky at first. We're going to focus on molar solubility, and then when we get that number, we can definitely convert it to little s solubility and convert moles into grams. And in that case, we have to multiply, right? Multiply by the molar mass. Okay. Up here we had to divide because we were going from solubility to molar solubility. Okay. So listen carefully. This S is literally the amount of solid that is ionized. The amount of solid that is ionized. So it's going to be a small number. Just like a lot of our KSPs are going to be tiny, this is going to be a small number. And I think the utility of this is to finally get actually the grams per liter, but that's neither here nor there. That is also actually the concentration of the ion if it has a coefficient of 1. The way you set up your chemical reaction is you have 1 mole of salt, and then it dissociates. So again, one more time. If that has a coefficient of 1, any of these ions, then that concentration is the molar solubility. And you'd put S right here. So what you want to put here is Ksp, and then we're going to substitute, right, the concentration. How much of this dissolved or ionized is telling me how much of this we have. That's S. And then this is the same concentration, S. So this equals S squared. If you're given, right, if you're given Ksp, then you can figure out the solubility, the molar solubility of silver chloride. So you solve for this. Now the thing is, you know that there's some salts that give an unequal amount. So if this was, I don't know, zinc chloride, you have one zinc, two chlorides. Well, zinc will be represented by S, and the chloride will be represented by 2S. The 2S goes in this parentheses down here, and don't forget, there was a 2 there, right? Then that would be squared as well. So you see it twice. You see it within the concentration, 2S, and you also got to square it, raised to the power of 2. Let me show you an example. And then, like I said, next video will be the practice problems. See examples. Okay, we have a Ksp for silver chloride, or we showed you the expression. Why don't we take one where, yes, we do have an unequal number of ions. Copper hydroxide, okay? You got to do 3 things. Number 1, go ahead and write out the equation, chemical equation, reaction. You have to know your charges. You could get it from here. Hydroxide is -1. In this case, copper has to be 2 plus, aqueous, plus, ooh, almost forgot. You have 2 hydroxides. They break up into separate hydroxides, and this is, again, aqueous. 2. Want to write the Ksp expression? Ksp equals the concentration of Cu 2 plus times the concentration of OH minus squared. Again, or maybe not again, but I want to emphasize that that is the concentration of OH minus. You don't put the 2 right now, okay, or anywhere except for the exponent. But we do know for a fact that every time we get 1 copper ion, we get 2 hydroxide ions. And that's where we're going to see that. We're going to see a 2-to-1 ratio. Because now you're going to substitute S into the concentrations. Solubility, okay, that has a coefficient of 1, so that's S. And then the concentration, right, of OH is actually 2 times the concentration of copper, and that in parentheses is squared. And then when you go ahead and expand it or combine terms, you have 4s cubed. And again, if given this, you will solve for s. And once you get s, right, you can go ahead and get little s in grams per liter. What is essential, as you could probably tell, is could you write this expression properly, and do you know how to substitute s into the equation? Let's try a harder one, the one that is very mysterious because I'm not telling you what the metal is, and I'm not telling you what the anion X is. But based on the subscripts, we know that we're going to have a product that has 2 M's and 3 X's. We're going to follow the same 3 steps. You see the 3 steps here? Ultimately, I want to know if you could get this Ksp equals to what term. So go ahead and pause your video, and when you're done, come back and watch how I would do it. Okay, number 1, M2X3 solid goes to, we've done this before in a previous video, 2M 2M 3 plus aqueous plus 3x X2 minus aqueous. Number 2, Ksp. This is going to be a little bit more complicated, right? Because we have coefficients. And put this in square brackets because that indicates concentration in molarity. And that's squared. And this is cubed. So here's the new information. How do I put in S in this equation? Ksp. S really is how much of this is dissolved, or how much of this is, we could say, dissociated. And every time this dissociates, right, we form 2 moles of M, 3 plus, and 3 moles of X2 minus. The molar solubility is what is the solubility of 1 molar, or 1 mole of this. So we're just going to use that as S. But now we have 2 M's. So this is 2S squared. Okay, there's the squared. Times 3S cubed. Oh, and we expand it. 4S, big S, squared times 3. No. Times 9. No. Oh man, 27? Is that really right? 3 times 3 is not 27. I did this wrong in class the other day. 27S cubed. Is that right? 3 times 3 times 3, and then S equals. This got out of hand really quickly. 4 times 27, 108 S. Again, I just want to remind myself that this is big S. S to the 5th. I wonder why no one corrected me in class the other day. That's correct. I'm just curious if, that's such a big number, but does it really matter when you have solubilities that are very, very tiny? We're going to leave it at that. You know what? I am going to find a problem in the textbook, and in the next video we are going to convert. We are going to solve for most likely solubility, molar solubility, converted to solubility if we are given a Ksp.